Hello. In this lecture, we finally proved the major theorem that we've been working towards, and that is this Cauchy convergence criteria theorem. In the previous lectures, we proved these two lemmas, which will be needed in order to prove this, which states that a sequence of real numbers is convergent if and only if it is a Cauchy sequence. So it's an equivalence. Right? If you're going to be convergent, then you must be Cauchy. If you're Cauchy, then you're a convergent sequence of real numbers. So what are the lemmas that we're going to use? We're going to use the lemma that we proved where we say that every convergent sequence of real numbers is Cauchy. That was a rather simple proof. Then we're going to also use that Cauchy sequences are bounded. So Cauchy sequences of real numbers are bounded. And then also we're going to use our famous Bolzano-Weierstrass theorem as well, which states that every bounded sequence has a convergent subsequence. So before even writing the proof of this, you can kind of get a sense of how the proof is going to go just by looking at the tools that I've put up here, right? So this is a biconditional statement. So we have to show that if it's convergent, then it's Cauchy. If it's Cauchy, then it's convergent. Well, by lemma 3.5.3, all convergent sequences of real numbers are Cauchy. So that's actually one of the directions already proven for us. So then, because that direction is satisfied by that lemma, proving the converse, we suppose that we have a Cauchy sequence, and then that Cauchy sequence is necessarily bounded. Since that sequence is bounded, by the Bolzano-Weierstrass theorem, it has a convergent subsequence. Once you have a convergent subsequence with some limit, then it could be possible or desirable to show that the sequence itself converges to that limit that we find as a consequence of the Bolzano-Weierstrass theorem. So let's go ahead and start piecing this together. A sequence of real numbers is convergent if and only if it is a Cauchy sequence. So we can say if X is a convergent sequence of real numbers, okay, convergent sequence of reals, then X is Cauchy by lemma 3.5.3. Okay, so that's what we just stated, right? So we just have to consider the converse now. Conversely, suppose X is Cauchy. The Cauchy sequence of reals, but for brevity, I'm going to write Cauchy. So then by lemma 3.5.4, then X is bounded by lemma 3.5.4. Okay. And then we're going to state the Bolzano-Weierstrass theorem by the Bolzano-Weierstrass theorem. X has a convergence subsequence. Maybe we'll denote it by X prime. Convergence subsequence, I'm just going to abbreviate it. And I'll use the standard notation n sub little k, like that. And then I'll say where X star is equal to the limit of that subsequence. Okay. So now our goal is to show, our hope would be to show that now we have some type of limit, right? And we're going to try to show that this sequence converges to that limit there. Okay. So, all right, how are we going to do that? So maybe I'm going to say it's like something like since X is Cauchy, for epsilon greater than 0, there exists some index h, right? So all that is some index such that m and n greater than or equal to h imply the distance from these terms is at most epsilon over 2. Or epsilon, it doesn't matter in the end. Just happens to be, if you want to be fancy, you can guess ahead of time. You're going to have to add two things that are bounded above by epsilon over 2. Okay. So what's more now is that we have the limit of the subsequence converges to X star, right? And we know that for all n and n greater than h, the distances between the terms is at most epsilon over 2. So what this is saying is that, okay, as the indices get larger and larger and larger, that gets closer to that, and these get closer to each other. This intuitively should also suggest to you that the sequence converges to that limit. So we can say, moreover, maybe, there is some index, I'll call it capital K, that's in the set of all the subsequence indices. So 1, 2, dot, 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 in sub little k, dot, 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 to infinite set. There is some index in there with, say, k greater than or equal to h, so that the distance from x sub k to x star is at most epsilon over 2. Now, why is that? So recall, so this is not a part of the proof. I'm just going to remind you that since this subsequence converges to X star, there is some like, what can I use? Like, I'll use like N or something. So since the subsequence converges to X star for epsilon greater than 0, there is some index capital K or capital N, so that n sub k greater than or equal to capital N implies the distance from the subsequence, the limit, is at most epsilon over 2, or epsilon, whatever you want to choose, right? But this is for every index in that sequence greater than or equal to n. Okay? So since this index for this pair H is fixed, and this is an infinite set of increasing indices, there is some index in there, k, greater than that H, so that the distance from that term to the limit is at most epsilon over 2. Okay, so hopefully that makes sense to you. Okay. So then, maybe we can say, what can we say? What can we say? Well, I can say this. Then for all n greater than or equal to k, x sub n minus x star, okay, is at most, so what can we can add and subtract x sub k. That's what we want. That thing, right? Or subtract and add. So yeah, so x sub n minus x sub k plus x sub k minus x star. Hope you can make out that plus symbol. That's a k right here. So all I did was that same old trick where I subtracted x sub k and added x sub k in there, and then applied the triangle inequality. But k is greater than or equal to h, right? And anytime these two indices are greater than or equal to h, n and k are greater than h, that is at most epsilon over 2. And this term here is at most epsilon over 2. So whenever n is larger than that k, we get that the terms of a sequence R and D arbitrarily close to the limit of that subsequence. So we're done. Hence, the limit of the sequence equals x star. And so x is convergent. Done. Okay. Now again, these techniques that we've been using, these are all very similar to things we've done in the past, and everything is building on itself, and that's kind of the nature of real analysis. The techniques stay the same, but the theory builds quite a bit. And I think that's one of the reasons why students find analysis difficult, is that you have to just immerse yourself in all of each piece of the course. You can't like forget about things. Okay. So thank you for watching. I hope that you enjoyed this proof.